021050 UTC, June 1, 2009. 2 degrees 59 minutes north, 30 degrees 35 minutes west. Deep over the Atlantic, Air France Flight 447 is cruising in darkness at 35,000 feet. Inside the cockpit, an unexpected alert suddenly chimes. The autopilot has disconnected. The crew has less than 3 seconds to react. On June 1, 2009, all 228 occupants aboard registration F-GZCP were lost. The aircraft did not suffer a structural failure, and the engines were functioning perfectly. This crash was the result of a fatal intersection between a temporary hardware glitch, advanced computer logic, and a sudden collapse in human cognitive awareness. The sequence begins as the Airbus A330 enters the Intertropical Convergence Zone, a band of intense equatorial storms. Here, the aircraft encounters high-altitude ice crystals. According to the French Accident Investigation Bureau, the blockage of pitot probes by ice crystals in crews was a phenomenon that was known but misunderstood by the aviation community. A pitot tube is a forward-facing sensor mounted on the outside of the aircraft. As the plane flies, it captures incoming ram air pressure, which the onboard computers use to calculate the aircraft's physical airspeed. This technical diagram from the investigation shows exactly what went wrong. The specific geometry of the Thales Type AA probes installed on this aircraft allowed dense, high-altitude ice crystals to overwhelm the internal heating elements, pack into the chamber, and completely blind the sensors. This hardware vulnerability was well documented. An internal Airbus memo from July 2002 warned that these specific Thales probes could be obstructed by ice. Air France had actually started replacing them across its long-haul fleet on May 30th, just 2 days prior. Flight 447 had not yet received the new probes. By freezing over, the probes laid a trap. The aircraft's computers suddenly lost all reliable airspeed data. Unable to safely manage the flight without this critical metric, the autopilot handed a degraded, manually operated aircraft back to a completely surprised crew in the middle of a turbulent night. When the A330's flight computers detect conflicting airspeed measurements, their logic dictates an immediate self-preservation measure. They downgrade the operating software from normal law to alternate law. Alternate law is a degraded software state. In normal law, the computers actively intervene to prevent a pilot from pushing the aircraft past its aerodynamic limits. In alternate law, those automatic protections are stripped away. The computer will allow the pilot to stall the jet. Startled by the sudden autopilot disconnect and erroneous speed indications, the pilot flying pulled back on his side stick, commanding a sharp, sustained climb. This drastically increased the aircraft's angle of attack, the critical angle between the pitch of the wing and the oncoming air. When that angle gets too steep, the wings lose lift. This schematic shows the trimmable horizontal stabilizer, a control surface that automatically shifts to balance pitch based on pilot inputs. Because the pilot held the stick back, the stabilizer automatically trimmed itself to 13 degrees nose up, locking the aircraft into a deep aerodynamic stall. The automation did not malfunction during this phase. It functioned perfectly within the programmed rules of alternate law. The tragic result is that the flight computers optimized the aircraft's tail surface to execute the pilot's doomed, stall-inducing commands. The environment inside the cockpit devolved into sensory overload. Dozens of error messages flooded the monitors. A synthetic stall warning sounded continuously. For 54 seconds, the warning blared, but the pilots made no verbal reference to it. In total, the specific word stall blared through the cockpit 75 times. Captain Dubois, who had been on a routine rest break, rushed back onto the flight deck just 1 minute and 38 seconds before impact. He found his co-pilot struggling to maintain control and immediately asked what was happening. Despite the blaring alarms and the physical shuddering of the airframe, the crew never understood they were falling. Their mental model of the flight was entirely divorced from the physical reality of an aircraft plunging toward the ocean at over 10,000 feet per minute. The final report by the investigators revealed systemic gaps far beyond the cockpit. The pilots flying the A330 that night had never received specific training for handling the aircraft manually at high altitudes, nor had they been trained to recover from an approach to stall while in alternate law. The hardware certification process was equally flawed. Historically, the standards used to test pitot probes did not adequately replicate the severe density of ice crystals found inside high-altitude equatorial storms. Following the crash, European and American aviation regulators took definitive action, mandating the total replacement of Thales Type A probes with more resilient models across all long-range Airbus fleets. The loss of Flight 447 forced the aviation industry to confront the automation paradox. When systems become so reliable that human intervention is rarely needed, pilots lose the manual skills required to save the plane when that automation abruptly quits. This analysis is based on the findings of the French Accident Investigation Bureau. It is intended for educational purposes, not professional aviation instruction, and is presented with deep respect for the victims and their families. The stall warning called out 75 times, and the cockpit never answered. 228 lives, one frozen